Welcome to the Energy System Engineering Seminar. This is the third we're hosting this spring. But this is a major first for us. This is a hybrid session. We haven't had this for ever. But we used to have live sessions about two and a half, 3 years ago. We're in a hybrid session, and thank you Abdul, for helping us out. But we have a very interesting talk today. And before the speaker comes on and talks, I'd like to have Dr. Urban talk with the students.
So where should I stand so I'm visible hybridly? Okay. So thanks, Rudy. Just wanted to take a minute to welcome Aron Patrick, our speaker today, and just talk a little bit about what I see as not just this particular opportunity, but more broadly, and put it in a bit in the context of the strategic plan work that we've been doing. I see tremendous opportunity for Lehigh to be partnering in the research and development kind of domain with outside firms, places like PPL, healthcare providers in the region, other companies in the region and nationally. I think we need to be looking for ways in which we can develop strong relationships, strong mutually beneficial relationships with partners, and then also look for ways in which those partnerships are not just about one thing, not just about kind of a research project, not just about students, kind of the student talent pipeline into companies, but really a broad look at the relationships we have with outside partners. Because we as a university, we are not, we shouldn't be, and we really can't be an ivory tower. We need to be engaged with what's happening in the world, what's happening in the region, in ways that will benefit us in our research, education, and service missions. Had a conversation with Aron this morning about some of the things that the way he's looking at the role of PPL and the kind of research and development efforts that PPL is putting together. I think there's tremendous amount of synergy with the way that he's thinking about this and the way that we're thinking about these kinds of partnerships at Lehigh, as well as in the particular topical and content areas. So I'm really excited to hear what he's going to talk about today. So I'll turn it over to Rudy. Thanks.
Thank you, Nathan. So again, before I introduce Aron formally, I just want to let you know that what the ground rules are, which is the same for all our seminars. After the speaker finishes, we have questions and answers, and we have give first shot to all the students. So we have several ESE students here and several remote. In fact, the remote audience has really grown. We have a mix of faculty, students, and industry personnel who are also on the call. So right now it's up to 35. We probably will end up around 50 or so, along with you guys. So let me introduce the speaker. I had a chance to listen to Aron once before in one of our classes, and I'll tell you, he's one of the rock stars in the utility R&D world. Thank you, Aron. I heard your talk before, and it was just very interesting. I think you're going to be changing the nature of how utilities do R&D. The very fact that you said you're opening up your data, utility folks, were scared, about talking about their data because for whatever reason. Aron is the Director of Research and Development for PPL Corporation. It's a leading U.S. energy company focused on providing electricity and natural gas safely, reliably, affordably, and sustainably. That's the fourth leg that is really important for all utilities today. And there are 3.5 million customers, and they're located in Kentucky, Pennsylvania, Rhode Island, and Virginia, so quite a big swath. PPL's high-performing award-winning utilities, Kentucky Utilities, Louisville Gas and Electric, PPL Electric Utilities, Rhode Island Energy, are addressing energy challenge head-on by building smarter, more resilient, and more dynamic power grids and advancing sustainable energy solutions. Aron's responsible for managing an enterprise-wide R&D strategy and PPL partnership with external research organizations, including national labs and universities. And that's really been the subject of his talks all morning today. He worked for PPL and PPL subsidiary LG&E and KU for more than 6 years. Before LG&E, you held leadership roles at Kentucky Energy and Environment Cabinet, including Assistant Director and Program Manager. Aaron was an intelligence analyst. And for the federal government, using statistical analysis and modeling to address national security problems. He's a Lexington native. He holds a bachelor's and master's degree from the University of Kentucky. Aaron, this is all yours.
It's humbling and embarrassing to hear my bio read. I am as you said, so I'm a Kentucky native, and the slides that I've got today are just a quick kind of preview of all the research projects we've got going on in Kentucky. We have about 140 of them. I'm not going to talk about all 140 research projects, but I do want to say one thing to you all, which is I want to come back in a year from now, and I don't want Kentucky slides. I want Lehigh University partnership slides that I can carry around to other schools in the United States and say, look what we did at Lehigh. That's the plan, guys. So let's, as I'm talking, don't worry about necessarily what we did in Kentucky, but I hope it tells you something about us as a corporation and what it is that we want to accomplish in the future. And I hope that you guys will come up with the ideas for how to make our world really a better place. That's what we're trying to do. So you guys know PPL Electric Utilities, obviously, here in Allentown, and the PPL general offices right there downtown. But I want to jump real quick. It's kind of funny where I usually am. People are like, where's that building? Where is that? I've never seen that, but you all have. Rudy already introduced us, but our mission is safe, reliable, sustainable energy at the lowest possible cost. That's a pretty big mission that encompasses a lot of stuff. Obviously, we include PPL EU, Kentucky Utilities, Louisville Gas and Electric, Old Dominion Power, and Rhode Island Energy. And we may grow in the near future. We've got a lot of strong partnerships so far. So these are partners we're working with in Kentucky. Everything I'm going to talk about today is Kentucky. Like I said, next year will be the Lehigh University version of this because we're going to do some amazing things. I'd say 90%, 80% of our projects are funded by the federal government in some way. So why? Why do we go after federal funding? Well, because we can only do so much. You can only do so much as a school. We can only do so much as a company. But we can team up with federal entities and national labs. We can do a lot more. We've got several research projects that are taking place at national labs, as well as at the Electric Power Research Institute. We are leaders of the EPRI Low Carbon Resource Initiative. And we're also leading investors in the Energy Impact Partners. It's our sort of a venture capital R&D arm that we have. Most of the projects that I'm going to talk to you today about, though, are actually in partnership with the University of Kentucky. If I had to size everything on here by dollars, that US DOE logo in the middle would just dwarf the entire slide. But if I had to size this by heart and soul and real boots on the ground, that'd be our University of Kentucky partners. They're the ones that make everything happen for us. We've got, we're working with leading technology firms like LG Chem, Greensmith, Bright Knight, but our footprint is pretty diverse. We've also got over there on the left, Shaker Village. What's that? It's a farm, and they have farmers and shepherds, and we hired them to manage our solar sites. Roundstone Native Seed. Yeah, we've got a team of about 10 that are working on native pollinator habitats and growing, and we've done hundreds and hundreds of acres of pollinator habitats. So R&D is pretty big for us. It's electrical engineering, it's chemical engineering, and it's planting seeds and managing livestock all across the board. I don't care if it's a 5,000-year-old technology. If it improves safety, reliability, and lowers costs, I'm in. Let's go. I'm going to have several links throughout the presentation, but open invitation to join our team if you'd like. Is there a way I can make this thing go away up here? Yeah, I don't know how, but okay. Well, anyways, So I think the titles are probably the most important. Yes, that's Chad. So Chad's been interning with us for the past couple of years, and Chad is now a research engineer full-time. Everyone that we hire in my department, we hire through our intern program. So basically you come in as a student and you work for a few years as a student, and then you transition full-time. That's how we do it. I like it because it gives the student an opportunity to see what we're all about and work on our projects. And it also gives us an opportunity to get to know the student. But Chad's been a really great example. You can email Chad or me if you have any questions about our internship program. We are hiring 3 interns just for my department right now, one of which I have required to be in this area. So we have a spot for someone in this area. Our corporation and our different companies have hundreds of intern positions open right now. So please, go to the PPL website and check it out. If you have any questions, don't hesitate to reach out. So if I can keep going here. So I want to talk about R&D timeframes, and this is a tool that I like to use. This is not as interesting as pictures of sheep. We're going to get there, guys. But first, I kind of wanted to frame this discussion in this tool. And we talked a little bit about this morning, but there's kind of this legacy R&D focus in the utility space that's 140 plus years old. And that's, how do we make coal better? How do we make coal cleaner? How do we reduce coal emissions? And then there's this modern space. Modern is solar, wind, lithium-ion batteries, electric vehicles. And we have future and distant future. One of the easy ways that I evaluate proposals that come to me for projects or proposals for technology is I ask myself 2 simple questions. And with these 2 questions, I can generally categorize a proposal into one of these 4 spaces. Can I build this thing now? Can I go out and do it right now? That's the first question. Second question is, does it make economic sense to build it? Does it lower costs? So for example, coal-fired power plant, that's not a thing anymore. You're not going to be able to build one for a variety of federal laws and other reasons. You can't build a coal plant. So no, I can't build it. I can still run it, and it might still be economic to do that, but you can't build it anymore. Modern, this is stuff that, yes, you can build it right now, and yes, it makes economic sense to do it. So Lehigh is apparently getting 2 megawatts of solar. That is awesome. That's a great example of can be built and is economic to do it. The future technologies, those are ones that we can build, and I'm going to talk to you about some of those that we are building already, but they're not economic. That's carbon capture, green hydrogen. And why are we researching those? To make them more economic. That's our goal, is to lower the cost of those particular technologies. And then we have distant future stuff. Fusion, for example, always going to be the distant future. I made a decision about 5 years ago. I'm not doing coal-focused research anymore. Period. We're not doing it. Shortly after that, our president and CEO, Ben Sorgi, he made the decision that we're not going to operate coal plants anymore. It's not part of our future. It's not part of our future as a country. It's not part of our future as a company, and therefore you don't need the R&D team looking at it. So we've kind of let that part go. I'm also going to forget about the stuff that's happening after 2050. Not that it's not good, and I'm sure it'll be fabulous, but it's just not in our lifetime, so I'm going to let that go. I'm focused on the here and now, very near future. If, as a country, we were happy with just providing the services that we're already providing, I might just look in the modern space. But because we've got goals, we as a company have goals, and the country has goals to decarbonize, we need some of the technologies from the near future horizon. So I'm talking about Kentucky. So this is some Kentucky data. But this is a look at sulfur dioxide emissions. Kentucky reduced sulfur dioxide emissions by 93% since 1995. That's pretty awesome. It didn't happen, though, because Kentucky wanted to. We as a country put together laws and set goals. But then our company in Kentucky Utilities, went out and did it. Went out and accomplished this task. I imagine whoever had my job in the 1950s and the 1960s, this was their challenge. We knew as people that sulfur dioxide was bad and that it needed to be stopped. And someone had to research how we were going to get rid of sulfur dioxide from coal-fired electricity generation. We did it. And as you guys probably know, we did it through flue gas desulfurization systems, aka scrubbers, that remove the sulfur dioxide. Does anybody know what percentage of coal is sulfur? Any wild guess?
2%.
That's a good number. 2% is probably right in the middle of what I would call high sulfur versus low sulfur. Here, you all have amazing coal, actually, really high carbon, low sulfur coal. That's about going to be less than 1% sulfur content. Cheaper coals, Illinois basin, what they have in Texas, they call coal, I think it's more of a rock, but you know, higher sulfur contents, 3-4%. But anyways, we set out to do a challenge. This is sort of a legacy R&D focus, eliminate sulfur dioxide. But the scale, I want to talk about the scale of the challenge. It was removing 1% of the piece of coal. We had this 1% sulfur, 2% sulfur that we had to get rid of. And we did it mechanically, chemically. It was very expensive, about $1 billion per plant, but we did it. This is yesterday's R&D focus. Today is CO2. This is a whole new challenge, folks. Our company, we electrified a lot of Pennsylvania 100 years ago. We electrified Kentucky, Rhode Island 100 years ago. We had some big challenges. We've built dams, we've built power plants, and like I just said, we eliminated sulfur dioxide emissions. Those were big challenges. No challenge we have ever faced is as hard as what we're setting out to do right now, which is eliminate carbon dioxide. Why? Why is it so hard? Like I said, coal has 1% sulfur content. What about carbon? Well, guess what? Coal is carbon. That's why you burn it. That's why you dig it out of the ground, because it's carbon. The French word for coal, charbon. In many languages, the word for coal is carbon. And so to say, I'm going to remove the carbon from the coal is like, boom, that is a huge engineering challenge. Now, fortunately, we as a country, we actually are on a good path. And again, I'm using Kentucky stuff. Sorry, I'm a Kentucky boy. But Kentucky hovered around 100 million tons a year of CO2 from electricity generation, and we've reduced that down by 40% just in the past 2 decades. That's remarkable. That's awesome. It wasn't because of carbon capture, though. We've done some renewables, a little bit of renewables. But what do you think is really driving it? What? Natural gas. Yeah, that's it. That is how we've achieved those reductions in the past. So that's our research focus. I won't stick on this slide because it's too texty, and I want to move on to some photos because I promised you some pictures of some sheep. But this is our focus, guys. We have set a promise. We have set a goal to decarbonize by 2050. That is huge. I get it. I get the scale of it, but we're going to do it. We've done it. I'm sure someone in the 1950s and 60s said, hey, whoa, it's too hard to get the sulfur out of the coal. We did it. We're going to do it with carbon as well. We will eliminate carbon dioxide emissions from electricity generation, period, full stop. I'm here at Lehigh because I'd like you all to join us in this effort and try to make this actually happen. So I've got some photos, tons of photos. This is one of the projects that I love the most, our pollinator habitats. This is not something like the size of this table. I don't really know how to tell you in terms of scale, but we have a several-mile hiking trail that goes through these properties. I don't know how it happened. I can't believe they let me do it, but I have a budget. And I was looking at it, I'm like, could we do pollinator habitats? And I don't know, I just did it. We just wrote some checks and started these pollinator habitats going. But there's a reason, there's a business need for it. First was, I was watching these solar farms and I noticed that there were people with weed eaters out there weed eating. So I know all of you have weed eated, probably like me. You've got this little gasoline powered weed eater, or at least I did before I replaced it with electric. You gotta choke this thing to make it start. You stand there, you break your back to start this thing. And then you get out there and you're weeding. Okay, this is kind of hard. This is kind of painful. But the other thing that you notice is that you stink after you run a weed eater. And it's not the grass. It's actually what's coming out of the back of the weed eater. So our cars have catalytic converters. Our power plants have selected catalytic reduction to reduce or eliminate nitrous oxides. Your weed eater is mixing oil and gas and just let it burn. And there's no controls. And the weird thing about it is it's right in your face. This thing is just like blowing in your face. It's actually CO2 emissions intensive. It's nasty. The other thing about it is it's labor intensive to weed eat. It was costing us a lot of money. So I started to ask, I'm like, how much are we spending on weed eating? And so, you know, the lawn care company does what a lawn care company does and tries to make it look like a golf course. And that's expensive. We were paying $95,000 a year to weed eat. There's also safety concerns. You know, you hire someone to weed eat. What if they hurt themselves? That's always our biggest fear. So we decided to stop weed eating. And instead take that money and build a pollinator habitat. We hired a botanist, a biologist, an entomologist to work with us on picking 64 native plants and wildflowers. This is very much a science project, guys. This was not just slinging seeds. Pick 64 native plants that will not grow taller than 36 inches because we don't want them in the way of the solar panels, and that would support native pollinators. You see in the photo, like in the bottom right, you can see it was a lot of these photos were kind of all taken at the same time. And the color down the lane is all one color. But if you were to watch it as a time lapse, it would be like a fireworks show because it's yellow one week and then it's blue and then it's red the next week. And every time you go, it's a different color. That's because we picked species that wouldn't be one and done in a couple of minutes or a couple of days or weeks. But we picked species that would intentionally grow throughout the season to support as much pollinators as we could. So the monarch butterflies, yeah, we've had an explosion in those, tons of bees. Everyone asks me, did you bring in honeybees? My answer is no. Why? Because there's bees that are already trying to make it. We don't want to bring in new bees to compete with them. So we're just letting the native insects just blossom. They've done really, really well. One of the things I didn't expect were all the birds, the finches. There's just tons of birds there eating seeds off the flowers and also eating insects, but it's really a beautiful place. My intern, Chad, he spent a lot of time taking photos, but this is some photos that he took. This is really pretty. This is an iPhone photo. I had to tell you something funny about this one, guys. I was on LinkedIn and I saw someone with this photo and it said, you know, professional pollinator, solar pollinator habitat services, call us. And this is a photo I took on my iPhone. And I like looked and I went back on my iPhone. I'm like, what? And it was like, I think at the time it was like my screen cover on my iPhone. I went back and I had like, you know, I had like 10 photos before and after this one, but there was a guy on LinkedIn selling pollinator habitat services with my photo, which I thought was hilarious. But anyways, yeah, it was a simple, just like click photo, but it was a beautiful day. That's another one of our students, Steven. And you can see like here, like this is kind of heavy with mountain mint and black-eyed Susans. But if you notice every different photo, there's different flowers blooming. It's been a really, really fun project. So moving on, you still have to maintain the site. So we still do need mowing. Okay, weed eating, I don't think it's cost effective. I don't think it's smart. I looked out at what other utilities were doing. Some utilities are building robots. One utility I went to, they use Roundup and gravel. And so they have a 40-acre site where they spray Roundup to eliminate vegetation and they've put gravel down to make sure nothing grows. And I'm like, oh my gosh, this is horrible. Like you're supposed to be, this whole point of this project, right, is to improve sustainability. You're gonna gravel it and then pour chemicals? No, stop the madness. Anyways, robots, that's expensive. Come on. It has to charge all day to run for an hour. Come on, we can do better than that. The answer was to look back in time. Different sheep here. The little lambs on the top right, those are Shetland ewe lambs. So those are native to Scotland. And then that ewe sheep on the left, that top left, she is a Katahdin. really beautiful animals. The Shetlands, they do make beautiful wool that gets, our shepherd does harvest. And then the Katahdins, they naturally lose their wool. One cool thing about that photo, listen, she's actually eating a flower. It's not new to have sheep graze grass. Honestly, Lehigh probably did it 100 years ago. It was kind of normal once upon a time. It's not new to grow flowers. What we did was a little weird though, is we picked pollinators that would support grazing as well. And I remember filming the sheep when we first set it out, and I was like, oh, I think she just ate like a $5 flower. It's kind of sad, but it was a really fun project. This is a GoPro shot that our intern Chad took of them. You can see they're seriously eating black-eyed Susans instead of grass. And this is kind of a before, and this is after the mowing crew comes through. Now, one thing you have to do, so you'll notice here that there's some little electric fence there. You might know why you have to do that? Because they're kind of like children. If you released them into the kitchen, into the pantry, they would go into the pantry and they would get the Doritos, and they would never get the broccoli. They would never eat their broccoli. So we do with the sheep, what we do is we confine them to initially 1 acre. Now they have about 3 acres. And we make them eat their 3 acres before we release them into the next section. It's all really planned. The crazy thing is we have a planning meeting that has to occur to determine when the sheep will go, because our botanists, our entomologists, the team that's managing the pollinator habitats, they're like really concerned about when the sheep hit. If you manage the timing of the sheep right, you can have them targeting invasive species. If you know when that invasive species is going to be predominant, and then you have times you need to get them off into a different section because you may need to protect a certain plant or insect. So there's quite a bit of science that goes behind it. Really fun project. You guys can watch this video later. It probably won't load, and I don't want to waste our time, but it is somewhere. It'll let me move forward. So this is Kentucky's largest battery. This is another fun project. And Rudy, I'm counting on you just to tell me when to stop talking because I have about 1,000 slides. But this project has been a ton of fun. Those folks there on the right, that was a former intern, now a research engineer. In the middle, that's a KO. He was a student intern with us at the time. He published a ton, and you can read a lot of the academic publications that he did on our battery site. Brilliant young man. We wish we could have hired him, but he was worth 3 times what we could pay. That's our battery. We are particularly proud of it. This is some different angles and views of the battery site. Obviously in the middle there, you've got our switchgear transformers and then inverters. So inverter, obviously switching the DC power to AC. We've focused quite a bit on safety because of lithium ion battery fires and explosions that have occurred. That's really our top focus. One of the things we did in 2022, so we'll never stop innovating, right? And prior to 2022, our battery sites had remote control. You logged in and someone kind of set the battery up and the rules in the framework. In 2022, after training so many people, I decided to automate it. The battery is now, we call it Autobot, but it is completely autonomous. It runs in Python, and it monitors a variety of factors, namely solar output, but also electricity demand and temperature, and it tasks and manages the battery by itself. One of the neat things about the site is we did lose connection to the site at some point. The fiber optic cable went out for whatever reason, but the battery had rules how to proceed in those circumstances, and it executes on its rules. For me, if I wanted to right now grab my laptop, which I've left somewhere, but if I wanted to grab my laptop and I wanted to log into the battery, going through the various VPNs and firewalls, it would take me like 10 minutes, 10 human minutes just to get into it. Then once I was in it, I had to do whatever I wanted to do. The nice thing on the Python logic and the AI that we designed this past year is that it's watching it in real time, and it can respond faster than we can and fix the problem. So it's much better than a human operator. This is a quick look. So I did promise you all that we've got cell level sub-cycle data that we're collecting. This is not cell level, so those are actually at rack levels. So each one of those colored boxes is about the size of a big refrigerator, but that's a section of batteries that contains 16 racks within it, and then hundreds of cells inside each section. But what we're doing here is we're kind of showing you a test of where we're varying power and output of the battery. One thing people don't think about when they operate big batteries like this is the temperature requirements. And quite frankly, that has been the biggest challenge to operating this battery, is keeping it cool. The battery on top is a little warmer always than the battery on the bottom. And specifically, it's the top row that's always warmer. And interestingly, it's because it's a design flaw. You have to look very, very carefully, but you'll notice here, there's space for air to flow behind the racks. And up here, there's an AC cabinet that someone, when the system was designed in Korea, they set it up this way that completely blocks airflow back this way. So this is a $6 million container right here. And so what we did is we went to Amazon.com and we bought a $5 fan and stuck it up on top and then largely fixed this problem. But we do monitor the battery in real time. Our solar farms and our batteries are now capable. One of the projects we did a few years ago is basically endowed them with the ability to send emails and texts at various intervals as they identify problems. So our battery real-time texts SOS if there's anything abnormal. So it has scripts monitoring different conditions. If it knows how to handle it, it fixes it. If not, it emergency texts a group of people that can jump in and try to fix it. A ton of publications. Feel free to check them out on our website. This past year, one of the other University of Kentucky projects is the solar car partnership. So we are funding the University of Kentucky to build a solar car. Quite proud of them. You can see there in the top left-hand corner them flying down the track. And I'm going to guess what speed they're going. Still a little bit of research left to go. They averaged about 28 miles per hour in that particular race, but they won first place, beating out MIT and other schools. So proud of them for that. But that's another space that we're looking at. We as a corporation, we've committed to be 100% electric of our light duty vehicles by 2030. So our EV research and solar powered EV research is all part of that. I didn't put pictures of them, but we do have a few solar powered electric vehicle charging stations, basically solar panels that are tracking and charging batteries and charging electric vehicles right below. So this is another really, really fun project. I unfortunately have not gotten to drive it as a max weight limit for the driver of 140 pounds. I will not be achieving that anytime soon, especially with all the dinners and lunches I do. Another project we kicked off in Kentucky, and again, I hope this is like giving you all ideas of what we're going to do next year. But this past year, we've got solar and battery recycling programs. So we did have an extra battery pack, basically a $10,000 battery that I just stole and drove to the University of Kentucky. They've broken that down and separated it out into its cobalt, its lithium, and nickel and manganese, et cetera, all into its source elements. Why is that important? Well, we just talked about coal. Okay, we're going to stop mining coal. Well, guess what? Your battery's got a lot of materials inside of it that are being mined somewhere. And it's really important that we know what we're going to do with all these batteries we're building when we're done with them. Are you just going to throw it in a landfill? That'd be really sad. So we're trying to recycle it. This may end up kind of in the venture capital space, I think. We've also got a solar recycling program that same thing. We've taken them several solar panels and they're breaking them down to their source elements. The challenge is economics. So the challenge is making it economic to actually do. We do have a few patents pending in that space. Carbon capture. So I think Kentucky's really, really great in carbon capture. This is really thanks to leadership from the Commonwealth of Kentucky investing in this technology early on. That on the left is our carbon capture site, one of our carbon capture sites that I manage at one of our power plants. It's about 20 stories tall. Actually, it's completely staffed by University of Kentucky employees. And this project has been very successful in seeking federal funds. Just in 2021 and 2022, we've been doing net negative power generation, net negative CO2 emissions power generation. So what do I mean by net negative? So rather than the power plant emitting, We're actually consuming from the direct air, CO2 from the direct air and mitigating those emissions. We're looking at converting coal to nuclear. I'm going to skip over these because it's kind of getting boring here. We've got on our distribution and transmission system, we've got studies, which are pretty interesting. So basically looking at how much solar can be integrated with the grid break. That's something we're pretty excited about. I want to show you some solar charts. So maybe pause. This is a chart I put together a couple of years ago. The colored bands show you what solar generation. But don't road rage. Who's ever on the phone, you shouldn't be road rage. The colored bands show you what solar should be doing by second of the day. So red is most likely, blue is least likely. Up in the top left-hand corner, you can see the specific day of the year and all the different parameters, like basically how much solar power we got at that particular moment. You'll notice in this picture that sunrise occurred a little after 8 a.m. and sunset was around 5:30 p.m. Of course, this was January 1st. I'm going to press play though and go through every second of the calendar year, day by day. Each little flick you see is a different day. And what you'll notice is as we move away from January, that red band or the probability of solar generation is growing. You'll notice sunrise occurring earlier, sunset occurring later. As we move into spring now, so now we're in April, we're moving into May, you can see the shoulders on the solar rainbow getting broader. And you'll notice it starts to develop a flat top. I call it its flat top, where it achieves its nameplate capacity and holds at 100% throughout the day. But what else do you notice about this besides the sunrise and sunset? So we're in July now, so we're exiting. So as we go back into summer, you're going to see the rainbow sort of melt back down. What else do you notice? Well, there's a black squiggly line in the middle, and that is what actually occurred. So the colored bands are showing you probabilities. So I used the normal Gaussian distribution function just to calculate probability by second of the day of what it should be. But the black line shows you what actually occurred. I'm going to go ahead and I'm going to let it melt away. It's got just a couple seconds left. Watch it melt down. It's sad, dark winter. And Christmas, winter solstice, end of the year. I'm going to pause it on my birthday, March 15th. I chose this day, not because it was just because of my birthday, but it's kind of emblematic of a problem with solar power. So we've all been sitting here in this room. Lights haven't flickered. Everything's been pretty good, no problems. Well, that's because somebody's managing it somewhere. PPL is managing it for you so that you have a nice steady power. If we just look at the output of this solar site, what you'll notice is around 9 o'clock in the morning on my birthday, solar power got up to 100%. And then a couple seconds later, it dropped off to 10%. And then it went right back up to 100% and then dropped off to 10%. What's going on? Clouds. I mean, honestly, that surprises a lot of people that clouds have that much of an impact. This would have been a beautiful day, guys. You would have bright sun, nice little puffy cloud rolling across your house. It would have been a beautiful day. It seemed like a great solar power day. But actually, there's a lot of intermittency that has to be managed. So I mentioned the Python script in the battery. That's what the battery is doing. The battery is watching this and trying to respond to it to mitigate it and to smooth it out. Very next day, perfect solar day, March 16th of 2017. Yes, my charts are old, but you see there, it got up to what, 10 a.m., 100%, and it held it essentially perfectly. Now we've got software doing what, MPPT, maximum power point tracking, trying to hold that perfect power all day long. But that was a day without clouds. Very next day, St. Patty's Day, rained. And that's what a rainy day on a solar farm looks like. Looks like what? We peaked for just a minute at 2 megawatts, 20% of the capacity of this particular solar site, and then dropped right back off. So this intermittency and challenge of predicting what it looks like, this is a big space that we need research in. So another chart I made same year. So that black squiggly line you just saw is right in the middle, but now I'm showing you Kentucky's combined electricity load by second of the day. What you'll notice is in the winter months, Kentucky's got a bimodal peak, early morning, it's cold, heater on, late evening, it's cold, heater on, and in the middle of the day, when the sun comes out, temperature goes up, heating demand goes down. And solar arrives at the party at the wrong time. That's the wrong time. That's when we actually need to turn power plants off. Now in the summer, it's the opposite. In summer, solar's at the right time to the party. And you can see that there's a little bit of dispersion between the two. So solar is typically occurring before peak electricity demand. And that's really because the sun is heating the building, it's heating the infrastructure, it's heating the air, and then the AC comes on to cool it. And there's about an hour or two lag. There's a lot of space, folks, for people to develop smart stuff, for one of you guys to develop some smart stuff that fixes that problem. Pre-cool the house. Dispatch loads like a dehumidifier or a water heater. Dispatch them in real time, instantaneously. This is something that you can do. A student could go and develop this product and probably make a lot of money on it that syncs this up. It's a big challenge. I got a lot of links. I'm not selling you anything unless you want a career with us. That'd be great. One thing I'm selling, I guess, is a career, but we do have, you can watch our solar dashboards in real time on your phone. I'm going to actually just look real quick so I can kind of see what solar generation is today. Curious if I have a good data connection. Well, we're kind of far away, but yeah, so we're putting out 1.4 megawatts. So we're at 14% capacity this very second. These dashboards live stream. They update every 10 seconds. This is the only solar site in the world that has the data live flowing to the public in real time. Same with our battery site. Our battery data is all exposed publicly, and hydro. It's all out there. So you guys can use it for various research. If I can, I want to talk to you about a paper we published with the University of Kentucky on Friday. This is one that I'm particularly excited about. Basically asking the question, how do we decarbonize Kentucky's electricity grid? There's a team of really smart people, several PhD students and a couple of professors that worked with us on this. And it took about a year, but I'm really proud of the work we did. There's been some studies that have come out that talk about making the United States 100% carbon-free and renewable. One of the most prominent is the Princeton Net Zero study, or the Berkeley 2035. There was another one, LA 100, that was done by the National Renewable Energy Laboratory. These are amazing studies. You should go read them. But I've put some emojis on here where I wanted to point out some things. First of all, on costs, Berkeley found that we're going to close all the power plants in the United States, build all new power plants, and it's going to lower costs. Wow, that's amazing. Went through it and kind of figured out how they did it. They really did it by calculating net health impacts. They also cheated a little bit in some spaces on fuel costs, et cetera. But anyways, they did an hourly study for sampled time periods. Kind of interesting. Princeton did find, same question, what's it going to take to go to net zero? They found it increases costs by $2.5 trillion, excuse me, for the United States to be 100% renewable. It's fascinating. There's this much disagreement in this space. One school says it's going to lower costs. The other school says it's going to raise costs. Well, guys, we don't even know which way is up here. We don't know which way is north and south. We got these schools telling us these different things. LA 100 did a fabulous report. I think the emoji I had for them was, oh yeah, it's a government report. So it had 1,300 pages. So our version of this report, which came out Friday, we did one thing I think is the real muscle flex here is we did minutely analyses. We used some pretty beefy computer systems to do it. The first reason that most people don't do minutely analyses, they do hourly analyses. The first reason is probably because they don't have computers that could actually run the thing. But the other reason is they don't have the data. Nobody has minute-to-minute data to know if the sun is shining or not shining at this minute versus the next. Hourly models that everyone's using, they are hiding something really important. What I just showed you on my birthday, this up and down, this real world up and down, in an hour, we can do anything. You look at like the problems the United States had around Christmas Eve this past year. In an hour, we can fire power plants on and get them up there. That's pretty easy to do. But in a minute, that's a challenge. And so these hourly models are missing the whole action. The whole game is being played minute to minute, second to second. And so I'm really proud of us for going at the 1 minute space here. So this is a quick look at some of the simulation results. This thing is really on my nerves. I wish I knew how to get rid of it. So what you can see here is we've got in gray our coal-fired electricity generating infrastructure. And in yellow, you can see solar coming online. One problem with a coal plant is this big, massive 20, 30 story tall structure is essentially burning coal to heat water, boil water, and make steam. That takes time. We call it, in power plant engineering, we call it a ramp rate, which is how fast a unit can ramp. Well, coal units can only ramp really 4 or 5 megawatts a minute. Meaning over the course of an hour, they could get to where they need to go, but minute to minute, they cannot do it. Therefore, in this particular simulation, as we add solar, that's the yellow, what you'll notice is there comes a point on that sunny week on the right-hand side where we are rejecting the solar power. It's being generated, but we're rejecting it. Why? Because we can't turn down the coal plant enough. So in this simulation, we're trying to answer the question, how do we get to 100% renewable? Well, first challenge you'll see is that with a coal plant, it doesn't integrate very well with a renewable resource. So let's change them all out. It's a computer simulation, so we can just click a button. And now we have natural gas combined cycle plants. They have ramp rates closer to 85 megawatts a minute. They can move very, very quickly. And what you'll notice in this particular scenario is that that same electricity generating portfolio can absorb and accept a much higher amount of solar energy than the coal portfolio could. No matter how much solar you add, though, you still have these things that occur around sunset until sunrise, called night. We had a reporter, guys, call during the solar eclipse. It was like a week before the solar eclipse. She said, "You all have solar power." Yes. And she said, "The solar eclipse is coming. Should people prepare for the grid to go down?" I said, "Ma'am, we've been doing this for 140 years and the sun has set every single day." And we keep the lights on. Yeah, so that was an epiphany for her. People don't realize, I didn't realize that snow blacked the solar panels. Some people don't realize that solar power doesn't produce power. It's probably obvious to you guys, but some people, that's new information. So what if we move off solar? In this particular scenario, we're integrating now wind and solar. One thing I like about solar or wind with solar is that they occur at different times. Wind is predominant in the winter. It's also stronger at night. Another way to think of wind is a nighttime solar panel. It's just a solar panel that produces power at night. So the two resources pair really nicely together, particularly in the winter. You notice that over on the left-hand side. So we ran all these computer simulations. I wanted to show you these charts because it kind of shows how it works. Oh yeah, Rosemary made these. These are great. So this shows, so that last chart just showed you 1 week. This chart is showing you minute to minute over the entire year with hours on our X and days of the year on the Y. And the red is now an imbalance, a grid imbalance where there's more power than the grid can absorb. On top, we've got solar portfolios, or on the left-hand side, we have solar, and on the right, we have solar and wind. And so you can kind of see how these problems occur as we integrate more and more renewable energy. If we package all that up, one of you guys knows how to turn that off, and I don't.
No, we don't.
All right, well, that's fine. On our x-axis there, we have 0 to 100% emissions reductions, renewables, whatever you want to call it. On 0, 0 there, that's Kentucky with no emissions reductions, just kind of doing same old, making America great again there. And then we have emissions reduction all the way up to 100% over on the right-hand side. The colors of the dots show you the technology combinations that we used. to make this happen. The gray is obviously coal-fired portfolios. We have one with coal and solar and one with coal and wind. We've got gas, and then we've got a bunch of zero carbon emitting technologies over on the far hand right-hand side. What I want to show you though, I want to highlight a few things. First, I want to draw a big circle around that space at 100% emissions reduction and zero cost. Anyone who is telling you that that is possible is lying. They are cheating, they are missing something. That is not true, folks. We can't throw away all the power plants we have in the United States and build new green, clean things and save money. It's not going to happen, at least not with the technologies we have and not with the way we use energy. There's nothing in that space. We've done combinations looking at technologies. The general trend is that costs go up. As you move over to clean and green, costs go up. Now, I've already told you, we're committed. We are committed to going 100% clean. We're doing it. Our challenge is making it cost effective, making it reliable. Other point I want to make, and you can read all this in the paper, but other point I want to make is that diversity is good for energy resources and for renewables in particular. What you'll notice is that if we, in our coal and solar only options, we can't really get past 20-something%. Why? Because you saw, we're just rejecting, we would need to, in these computer simulations, we would need to reject all the solar power that occurred at noon, and coal units would have to run at night. Meaning you can keep adding the solar, that's fine, but only thing you're doing is you're moving vertical on this chart, you're moving up in cost, you're not actually moving over, you're not reducing emissions. You see the red arrows though, that's pointing out where we switch and use solar and wind. You can go a lot further. So some people have this kind of like, kind of singular vision on renewables, and they think solar. And I'm saying, no, we need diversity of renewables. Here we did solar plus wind, but we could take this on, right? If it was solar, wind, hydro, geothermal, all these different fuels together, that's going to push us further and further to the right and keep us down off the cost dimension. So big lesson, incorporate multiple renewables, diversity of renewables, not all one thing. The other big lesson, and this is why people call it the bridge, is natural gas combined cycle. So we all want to be over there at 100%, and we're headed that direction. But the bridge to it, it's natural gas. Quite frankly, that is cheap. It reduces emissions. Switching from coal to gas reduces emissions by 60% right off the bat, even without renewables, without future tech, just current stuff. So pretty obvious. But the other thing, as I showed you in the charts, and this is why I like gas the most, is it pairs well with solar and wind, where coal does not. And so you'll notice that moving to gas, we have this emissions reduction by about 50% from where we are today. But it integrates a lot more solar and wind and takes us a lot further down on that spectrum. I kind of want to point out that there's some really bad paths. There's some mistakes that could be made. And here's one to point out. Keep your coal portfolio and build lots and lots and lots of solar. That's not smart. That's really not smart. From here to 20% renewables, okay, no problem. Sure, fine. Keep doing the renewables to 20%. But beyond that point, if you keep those coal plants, you're just throwing money out the window by building more renewables. So there's some mistakes, some big mistakes that can be made. It's not as simple as renewables are good, build all the renewables you can. We have to think about the other parts of our portfolio. Like I said, our distribution, our transmission hosting capacity, but also the fossil units. Like I already said, gas is a quick and easy fix to the problem. And then there's a lot of technologies in the 100% space, but what you'll notice about them is they're all slightly more expensive. And so we're looking at it, hydrogen, batteries, 24/7 batteries, carbon capture, but the combination of those technologies tend to be pretty expensive. The good news is for Kentucky, especially, not so much California, because California is already pretty far down this road. The good news in Kentucky is that with where we are in solar, we can keep building and we don't have a problem for many years to come. Probably around 2030, Kentucky's going to start to have some issues integrating if they aren't planning better, if we aren't planning better. So that was cost to build. I want to switch the y-axis on us real quick here and go levelized energy cost. Why? Because cost to build hides a very important component, fuel. In each of those cases, we were burning fuel, and that costs money. And now what you notice is that 0 to 20% space is a lot more flat, because each time we add a renewable, we reduce some of the fuel burn. And then what do you notice about the gas? So with coal, it clears really well, but what do you notice about gas? If you add gas, you should add a lot of solar with it, because solar pairs so well with gas, it reduces the amount of gas that you have to burn, ends up lowering your total cost. I think people's eyes are glazing over, so I'm gonna speed up here and then try to have some more discussion. And again, obviously there's a lot of stuff in the 100% space and it needs a lot of work. I will skip all of that text and just open it up to discussion. So that paper out Friday, you can get it there. If you want to see the slides, you can have the slides. If you want to just steal my GIFs, take them, they're there, have at it. And then you can see our solar dashboards and join our team, all from those links. But this is a lot of stuff that we've done in Kentucky. And like I said, the vast majority of this work was done by the University of Kentucky. And I want to do the same thing here with you all and with Lehigh. So I'm hopeful that I can stop talking and we can have more of a conversation. Does anybody have questions or something they want to talk about? Yes, sir.
You showed the cost in billions to do this. Was that just for this area that PPL services, or what was that? Was that the country?
That was just PPL Kentucky.
That was just PPL Kentucky.
Yep. Yeah, so you look at the Princeton study, they found 2.5 trillion in the United States.
Right.
Ballpark, yes, that's a ballpark, the correct number. This is dollar-wise bigger than putting a man on the moon. This is huge, what we're setting out to do. Decarbonize and move over to renewables, this is big. And that's why R&D is so necessary to make sure we do this smart and do it for as low cost as possible. Probably interrupted you, or you were on a train of thought there. No?
No,
No. Other questions? Yes, sir.
On your pilot scale projects for carbon capture in natural gas fired turbines, I'm assuming you use an MEA as a solvent.
Proprietary monoethylenamine. It's actually property of the University of Kentucky, so I have access to it, but they actually own the intellectual property there.
What can you share? What is the penalty on the reboiler side or the regeneration of the amine? It does a big burden on the natural gas that you would expect.
It is a burden on the system, and regeneration of the monoethylenamine is actually one of the biggest chemical engineering challenges of the entire project. Capturing the CO2 is easy, but doing it energy efficiently and doing it effectively is one of the big challenges. If you go to our Kentucky business, it's LG&E KU.com/research. We put all of the public papers. We have 30 patents on our carbon capture technology with the University of Kentucky, and over 150 peer-reviewed academic papers on carbon capture. Probably every publicly available piece of information you want on our carbon capture processes is available on that website, lgneku.com/research.
Ava? Yeah. Please introduce yourself.
Oh, yes, sorry. My name's Ava Hudson. I'm in the ESE program. It's my first semester. I was curious. Thank you for your presentation too, by the way. I was curious about the pollinator project. So
My favorite.
it's very interesting. I looked at doing one at Black Hills Energy in South Dakota, and so theirs was just for reseeding operations. So when they had done, construction for whatever it may be. So I was wondering if you guys also use native seeds and try to do that for those projects, as well as what your metrics are in terms of measuring the success. Because I know one of the complaints for Black Hills Energy was the employees were like, okay, well, how are we going to go and count the number of bees that show up, or like,
Yes.
how are we going to show the success? So yeah, I was wondering
Yes.
if that's what you guys do for that.
Yes, we hired a biologist to go out there and literally count bees. We also did at peak season. My team love hates. I'm going to tell you the truth, because some of them, they have PhDs and they're really, really sharp. And yet I'm like, guys, today we're counting bees. And so we did. We went out there with scorecards. We had some of the researchers that were really good in that space kind of give us the scorecards, coach us, and then we split up and we tried to score the different sections. We also have different controls in different parts and different seed mixes. So part of the scoring wasn't just was this project successful, it's like which part of the project was the most successful. Some parts with sheep, some parts without the sheep. It is cool, and we do have, I don't think it's on the website, but I will be happy to send you the reports that we have. There's 3 or 4 that have been put out on those projects, including our exact seed mixes. One thing I'll say that most people don't really understand, I think it led to a lot of frustration, is there's probably a 3-year lead time on this project. It's not you go out and put seeds and 2 months later you have flowers. If you do that, you've done it wrong. There's a lot of raking, a lot of site prep to eliminate Johnson grass and other invasive species in advance. What we did is we completely removed the vegetation using 4-wheelers with a special raking apparatus that was designed. And then we went in and seeded it with wheat, 100% wheat. And just made sure that it was only wheat on the site. And we cleared the wheat out, and then we planted pollinator habitats. If you didn't do that, you're going to have things that just keep coming up and competing. The nice thing is, though, with these plants is they're really hardy. If they can get 1 year in, then they're going to make it.
Right.
And so you need this 3-year lead time on those projects. We did an RFP to see who could do the best project, and we had third parties come in, and some of them were just construction companies that were like, yeah, I'm going to buy a seed mix, I'm going to throw it down. I'm like, there was a lot more involved in that to make sure this happens right. I don't know if I answered your question or not. I'm really
Yes.
excited about that project, though.
And then, so do you also do this at, when you have other construction projects and you have to revegetate, or is that more just
Yep.
the usual revegetate with whatever was there before?
No, this is something we're doing at, quite honestly, it's too bad we're broadcasting live here, but coal plants, guys, that's not real great on the ground and on the earth. Sorry, it's just not. So what we're doing mostly now is trying to repurpose the former coal sites as pollinator habitats. And so we're coming in and trying to plant species that will grow and will prosper there. It's a really sort of beautiful poetic justice to come back to a former coal site and just see all the different wildflowers blooming. So that's where we're doing it most. We are moving May 1st. The sheep are moving to their next site, our second site, where we've already done pollinator habitats there. And now we're moving in the sheep. So we're not just done. It's not like we did it, we took the picture, we're done. No,
Right.
now we keep going. Next site, next coal plant, next solar farm, etc.
Thank you very much.
Okay. Richard?
Hi, my name is Victor Wang, and I'm one of the ESE student here, and I would like to ask you, do you think the solar car is possible in the future? I mean, for the solar system, it has lower efficiency when compared to the coal and the natural gas. So how can you ensure the car generates power from the solar?
So state of the art that we have can do, like I said, 28 miles per hour in perfect sun forever. But as you saw from my charts, perfect sun doesn't last forever. And so without that perfect sun, maybe 40 miles. So 28 miles an hour for 40 miles. That's where we are right now, and you're gonna have to be 135 pounds. And you cannot even bring a bottle of water with you. I mean, so that's state of the art now. That's gonna keep evolving, that's gonna keep changing. Every year, the team's going further, faster. It'll come, I am sure, 2050s and beyond, it'll come. But it's quite a ways away. It's not something that you're gonna go out and buy in the next 5-10 years. You could, but you'd have to really love walking.
Thank you.
And
Hello, my name is Andy. I'm an undergrad work study student at the master's program. I was wondering what method are you using for the solar recycling? Because there's many like ways you can do it.
It's a patent pending process, so I can send you the patent. The patent application, it's all public. Honestly, I've watched it. And it's a giant grinder. Take the panel and just like crush it. Then once it's crushed, it's essentially baked, for lack of a better word, it's baked. And then there's magnets and it's all sorted out in the end, and the rest you'll have to read the formal paper. That's about as much as I know about it.
Hi, my name is Alexander Gardner. I'm a student here with the ESE program. My capstone project here is focused on hydrogen research,
Awesome.
production, storage, transportation. So I was curious what kind of research development things you guys are doing with that, or if there are any specific like large DOE grants or funds that you guys are using for your research. If you would talk about that.
Yeah, so we've gotten quite a few hydrogen focused awards. One this past month, about $3.5 million for a direct air capture with hydrogen production system that we're building with the University of Kentucky at one of our power plants. That system essentially, there's no flue gas. It's just being powered by wind and solar, and it captures CO2 and produces a stream of hydrogen, bottles the CO2 and it bottles the hydrogen. We have a few $1 million in federal awards on that one passed. So that's the one I'm most excited about. One I'm less excited about is the one that everyone's talking about, which is the hydrogen hub. We are, of course, leading the Kentucky's hydrogen hub efforts, and we're engaged in Rhode Island with the New York hub, and then Pennsylvania to some extent with the Appalachian hub. Those hubs are bigger, they're further out. You really don't start to see production scale of those until like the 2030s, and 2036 is when they're supposed to be up and running. That is so far away. That's why I'm more excited about the stuff we're building in 2024. There's some, yes, really big dollars being put in the hydrogen space.
What was the name of the first technology? So if I could like search it to read
Yeah,
more about it.
direct air capture.
Okay.
And there's some publications on our Kentucky businesses, LG&E.com/research. You can see all the carbon capture publications on that page. We don't have one on the Pennsylvania website yet, but we do. You can see the direct air capture processes. That's led by Dr. Ayo Omasebi on our team, and he and his team have been very, very successful.
Awesome. Thank you.
one end.
Hi, my name is Sean Coulter. I'm getting my master's in mechanical engineering now. I'm taking an ESE course on transmission and distribution. And I've been extremely interested in solar and renewables this whole time. I'm wondering, you said that you can break down the solar panels into their elements and try to essentially refabricate new solar panels from that. But is that at a point where it's cost effective to do it over buying panels yet or no? Okay.
I gave the University of Kentucky $100,000 to recycle 5 panels. The commercial cost to do that would have been $50. $100,000 to do it. So is it cost effective for them to do it? No. They're still going to try. In our startup space on Wall Street, I have interviewed startups that are pursuing the goal of around $15 a panel cost. When we started out, it was kind of interesting. So it was kind of fun breaking the panel down and figuring out what was in it. We found silver, like $1 of silver. There's copper. There's a couple dollars of copper involved. There are some elements, and I thought, kind of in the beginning, maybe there's enough in there to pay for this. There may be, and that's some startups are working towards $10, $15. Nobody's in the moneymaker space. I do. I have heard some nonsense that I want to talk about real quick. I've heard about people, saying that solar panels are going to pollute the water and destroy the land, and we've done a lot of tests. That's ridiculous, unless you pile them up and crush them. In which case, if you do, you pile them up, say in a landfill, so you take a whole solar farm and you put it in a landfill and they get crushed and the glass breaks, then yes, actually you are causing some sort of problem. As far as like farmers being concerned with solar panels, no. I mean, unless they were crushing them in a very concentrated place, no. But this is something we have to talk about. Solar panels have an expected life of 30 years. And I've seen many that don't make it 30 years. At that one site that I showed photos of, we've got 44,500 solar panels. And there's a bunch that need to be recycled every year. We, as a country, we have to have a plan. And I'm confident that all these solar farms that we're putting up now, not just us, but everyone around the world, people are going to come up with a way to do it. But right now they're targeting $10 to $15 a panel cost. Thank you.
All right, that was, sorry, yes, Jane,
Hi, Jade Sessions, ESE student.
speak up, please.
When looking at the overgeneration of renewables, wind and solar, that you talked about, how do you see storage fitting into this equation in the near future, considering just how expensive battery storage is at the moment?
So that's the first thing. So once you confront someone with the obviousness that isn't obvious to everyone, the sun doesn't shine all the time, the wind doesn't blow all the time, and therefore it's complicated. Everyone says, well, batteries. And you think, oh, okay, batteries. The problem is I like to look at things in levelized cost. Operating an old coal plant is going to cost you about $20 a megawatt hour, $20 a megawatt hour. New solar at its best in 2020 was around $25 a megawatt hour. But that's solar when the sun is shining, $25 a megawatt hour. Once we incorporate battery storage into it, we're now in the $500 per megawatt hour of power space. Batteries add an incredible amount of cost. We can back that off if we have a diversity of renewables. We can get down to say $300 a megawatt hour, but it is still tenfold, more than tenfold the price of fossil generation. So I'm confident that batteries are going to continue to get better. Right now they have depended, of course, the NMC batteries, nickel, manganese, cobalt, have depended on very rare and expensive elements, specifically cobalt. That's how we've gotten the energy densities with those NMC batteries. But that cobalt got up to, in 2021, up to $85,000 a ton. Really, really, really expensive. And also, sadly, quite a large portion of it is being produced by children in the Democratic Republic of the Congo. And so, you can kind of imagine someone that went out and said, I'm going to stop the coal mining. That's evil. I'm going to stop the coal mining. And they went to Tesla and they bought the Tesla battery pack and they installed it. And somewhere in the world, a child went down and mined into the cobalt. But battery chemistry is changing. Battery costs are changing. They continue to fall. So solar has had a little bit of a kind of a bounce back, like it fell down to $25 and jumped back up to $50. And now it's coming back down again. A little bit of a bounce there. But batteries have continued their constant improvement. Tesla and other manufacturers are moving more over to lithium phosphate batteries and away from the NMC. I'm confident that with changes in chemistry, or maybe something crazy obvious like gravity-based batteries where you just lift a rock up and drop it back down again, I'm confident we'll figure it out. Batteries are the obvious answer. It's just about, can we do it? Is it actually sustainable? I don't think that just doing batteries the way we were doing it in the 2019 and 2020 timeframe, which is go out and mine more stuff and put all the chemicals in a box. I don't think that's a sustainability solution. It's not cost effective either. So batteries is definitely an area for future progress.
I want to go to this remote audience. I know there's a lot of you out there. Please, if you have a question, please unmute yourself and ask that question. Introduce yourself. Remote audience, anybody?
Yes, Rudy, I have a question. This is Hal Long. Can you hear me?
Yep.
Yeah, so if we have a better distribution system across the United States, I'm thinking where you can distribute power easily across the United States with a more robust distribution center system, you could have wind at the coast and wind in the plain and solar in the mid states, and you'd have distributed over the United States. You would have it wouldn't be cloudy everywhere. It wouldn't be so. You'd have all this renewable power available in various parts of the country that could be used anywhere. Is that? I know you're thinking, just Kentucky, but if you think of getting resources from the states, go ahead.
No, you're absolutely right. If you just look at the sun, the way the sun rotates around the earth, I showed you charts in Kentucky, but if we looked at the sun on the earth, the sun's always shining somewhere. You're right. If there were high voltage transmission systems that could transect the entire planet, we could fix this problem. That's what's kind of exciting, right? Is that all of these problems are going to go away. We will fix this, whether it's a new battery or a new combination of renewables or a transmission system that ties everything together. We will fix it. Someone will look back in 100 years from now and be like, oh yeah, obviously they fixed it. But the exciting thing for us is that we're in the space where we have to figure out how to fix it. It's not fixed yet.
Right.
Challenges with transmission. So if you look at ISOs, so look at the SPP, Southwest Power Pool, or MISO, the Midwest and Intersystem Operator, or PJM here, Pennsylvania, Jersey, and MISO. You look at it, they have nodal prices, so prices at specific nodes within their transmission system. And what you'll notice is that there's extreme variation. Even in Texas, there are power just variations in power prices that go from negative $30, where they'll pay you have to pay if you're producing power, to other parts in the system where it's $10,000 a megawatt hour. And it's like, why is power so different 100, 200 miles away? Transmission, there's not enough transmission. They don't even have the problem fixed just in Texas. So it'll be fixed. I think you're right. Transmission is one of the ways. It's just not fixed yet. I will say one other thing. If you think about the highway system that we have across the United States, World War II, we went out and we decided, hey, we're going to build an interstate system. Was it Eisenhower or Truman, that era? We built all those highways. We don't have that same ability anymore in the United States to do stuff. We're not able to do big projects like that anymore. A transmission system is essentially a highway. And people are real mad anytime you come knocking on the door and say, hey, we need to build a transmission system through here for that renewable project over there. That makes people real mad. So it's definitely a possibility. It's just a lot of challenges, including people not wanting transmission in their yard.
John, you had a question, right?
Yeah, just the quick one, Aaron. In the future, we're gonna have, this more renewables, more solar, more wind. And it's gonna be a mix of companies like PPL building these farms and owning them.
Yep.
And private investors, individuals.
Yeah.
Jumping in, and I think the number of applications now for approval of solar farms is blossoming.
Yep.
Where do you see the balance of that? Is there a place for these
They're critical.
these small companies to exist, or are they going to get, dwarfed over time by you folks?
We're actually partnering with a lot of small companies. Our latest solar site that we built it with a really small company called Solar Alliance. They saw themselves as kind of a not-for-profit. They just want to make the world a better place, and we hired them to build solar farms. We're teaming up. We kind of all have the same goal. Our business is in providing reliability and low cost, and we're obligated in every state that we serve to do the thing that is least cost. We're what's called a regulated utility, a regulated monopoly. And we have an obligation to do the thing that is cheapest and best for our customer. And if we don't, the state has to review all of those decisions. And if at the end of the day, there's two people proposing a solar farm and one of them is $30 and one of them is 28, we are obligated to go with the one that's 28, whether it's ours or not. We need to build that solution. So there's definitely a space. Smaller companies tend to have more debt. Debt, when you're building a project, is a good thing. Because debt, you can get a loan for 1%, 2%. We have shareholders. Our shareholders have a rate of return that's higher than 1 to 2%. So heavily leveraged debt financed renewable operation can often come in with a project that's lower cost than we can. And in that case, we're going to select them and we're going to go with them. We're going to look back at this someday, guys, and we're going to have phones that just power themselves, right? Our great grandchildren, we're going to have phones that just power itself. I get that. And all these wires and all these power plants, they're probably not part of the future. But for now they are. So.
Eva, you had a question, right?
Yeah, I just was curious on the research that you guys have done, or like what you're doing with any SMR technology, like what your whole nuclear kind of portfolio is looking like.
I skipped that slide, I think for speed, but so at our Gent power station in Kentucky on the Ohio River, we are doing a partnership with Idaho National Lab funded by DOE on coal to nuclear conversion. Of course, the University of Kentucky is involved as well. We hope to have that report done by September, but basically the premise of the report is hey, we've got this power plant, we already own it. We've got this fence here, we've got the river, with all the things we need for a nuclear plant. Let's look at it, let's evaluate it. Honestly, when you rank order all the technologies from most obvious, which would be the next solar panel you were going to put in, to most expensive or least obvious, hydrogen, carbon capture, nuclear is somewhere in the middle there. So back to the $1 per megawatt hour, we can do solar at $30 a megawatt hour. Carbon capture, maybe 150, 200, maybe $400 a megawatt hour in some projects I've seen. Nuclear falls in the middle, somewhere around $100 a megawatt hour. So it's not step one, but it's also, a lot of people are fixated on these other technologies that are less obvious than nuclear. And I think we need to have a very common sense sort of walk from where we are to where we want to be. And some of the obvious steps in the middle include solar, wind, gas, and nuclear. Those things are all along the way before we get to hydrogen or carbon capture. Even batteries. Nuclear makes more sense than batteries.
You said that report is coming out in
September, just for that one. But Idaho National Labs has done some research on some other studies.
Thank you.
Just, you have a few questions on the text you want to show to?
Okay, let's pull these up. You want to govern these, or do you want me to?
No, go ahead. Pick the question you like.
I'm gonna go to the last one because it's probably the most interesting. All right, so CCS is geared towards capturing carbon emitted by coal and natural gas power and power entirely phased out, referred to as retirement. If the coal is retired, does this happen after return on investment or lifespan? So we're not doing any research on coal anymore. We've abandoned that. Carbon capture to me is part of gas. Why? Because gas plants need to be built now to transition the United States. It's the bridge. And I think all the gas plants that will be built with carbon capture technology. Also, don't think of carbon capture as only a point source or flue gas carbon capture system. Think about direct air capture. So it's not cheap. Again, I just said carbon capture is one of the most expensive in the stack. But what's exciting about it is the only technology that we have on the table that can reverse CO2 accumulation. It's kind of exciting. I want to learn more about. Yes, I will come to that next session. Oh, that's to everyone. Great. And Susan again. Cool. Don't understand all the questions. So, mistake of forcing end users to switch to electric heat and cooking instead of gas during many years. Take to transition to net zero. If you start with the premise, that you must decarbonize and we must move to renewable, then you have to get rid of gas cooking and gas heat. I'm not saying you should have that premise. Clearly, I've said that gas, I think, is a part of the solution as we transition from A to B. But I think the dream is 100% renewable powered world with no fossil fuels. And gas home heating is kind of a big part of that.
I think England is phasing out the fossil fuel heating system. They're pushing.
A lot of states are, a lot of states have already banned it. Including, like I said, Rhode Island, they've got a goal to decarbonize gas. So I need Lehigh to help me figure out how we're gonna do that by 2035, please. Y'all wanna team up with us?
I think we have time for one or two quick questions. Not let them go. Remote audience, anybody? Question for Aaron?
Hi, this is Avnay Sonkar from Mechanical Engineering Department. I basically work with the energy storage systems, but thermal energy storage. My question is PPL is considering any research towards concentrators, solar concentrators, because thermal storage is kind of much more easier, cheaper than electrical storage. So is there any kind of focus on that? Because especially since you mentioned about intermittent during the daytime, I think thermal energy storage actually is much more easier to deal with it than a battery, because when we're talking about big power plants, the size of the battery itself is like sometimes, at least at this point of time, it's kind of very unrealistic to have such a huge battery system.
So we're looking a lot at thermal energy storage. One of the problems is we've got a round trip efficiency in the 50–60% space typically. Don't usually see something better than that. A lot of the molten salt energy storage projects, particularly if you think about Ivanpah, or some of the big CSP projects, concentrated solar power projects that have occurred, the molten salt portion of it has been really kind of where there have been the most problems, leaks, etc. I think it's got a lot of potential. If you think about ice plants, there are ice plants that basically make ice and then they melt the ice or use the ice for cooling. Those make sense. They made sense in the 90s. Those are money makers. I think thermal storage on the heat side or the molten salt side, I think it's a big part of the solution as well, particularly when you've got rejected renewables. But what I've seen so far is I'm not sure that it's the most cost effective right now. One other thing I want to point out is on those charts I was showing with intermittent renewables, it's not just shifting power 12 hours forward, it's actually shifting power like 2 minutes. That's where lithium ion dominates. Fast round trip in and out. Thermal storage tends to have a slow start, then a slow spin back off, and pretty high round trip efficiency losses. But if it makes sense in the end and it's the right choice, then that'll be the one we do. It's certainly on the table. We're definitely looking at it. There's been some success in converting coal plants into big thermal energy storage sites, and I'd be excited if we could do that as well.
Okay, one last question. Carlos?
Better be good.
Develop on the DOE funding, thermal energy, thermal battery here in Lehigh. He used a combination of concrete, engineered concrete and thermal siphons, so we can move heat very fast. I mean, the idea was to get to a ramping rate when you integrate it with 4-5 power plants, so about maybe 5 megawatts per minute. And it's very fast. You can discharge in about 70% in about half an hour. And then the round trip efficiency, charge to discharge, not in the concrete, but media to media. Right now, we may be pushing around 85%.
That's better than lithium ion. Sounds like we need to work together on that. I got a lot to learn from you guys, which is why I'm here.
Well, this is a round of applause for Aaron. And really, some of the answers were segues into some of our future talk. We have a startup company called Malta. You may have heard of
Oh, yeah.
Malta. They're going to talk about long duration storage. Their CEO talked last year, so she's sending somebody else. We're talking about the whole part of the energy transition is long duration storage, plays a big part. And they've got a lot of funding, so we'll see what they have to say. But listen, thank you for your attention. And thank you, Abdul, for helping out. And thank you all in the remote world. And we'll see you in a couple of weeks.